Here's another example of something to prove. The 8th root of 8 factorial is less than the 9th root of 9 factorial. As usual, I'll ask you please to pause the video, spend a bit of time thinking about this problem, anything you can write down that might be relevant, anything you can work out from this, any sorts of logical procedures that might be important. Please pause the video. Okay, back again. So we've got here, let's do some rough working. We've got the 8th root of 8 factorial is less than the 9th root of 9 factorial. What can we do with that? Well, I'm firstly going to recap a lesson we had from previous proof, which is simplify. Simplify, I won't say always, but nearly always a good thing to try. Might not work all the time, but worth trying. How could we simplify this here? Now, I'm going to add a bit to that lesson and say if you're not quite sure how or what you should try and simplify, one possibility is look for the most difficult part and see if you can simplify in such a way to get rid of that. Now, you might take the point of view, you might have done this differently when you had the video paused, but you might take the point of view that the difficult things here are the roots, the 8th root and the 9th root. You might perhaps say, well, okay, to get rid of the 8th root, I have to take the 8th power of both sides. And okay, that's certainly simplified the left-hand side. Unfortunately, it's made the right-hand side rather worse. So you could say, well, okay, if I took the 9th power of both sides, then I would get rid of the 9th root there, but that would make this one a lot worse. Hopefully, after thinking about that for a little, you can come up with the idea, well, I'll take the 8th power and the 9th power. In other words, the 72nd power. Let's mark that with a question mark. Doesn't quite seem to be helpful. If I take the 72nd power of both sides, I get 8 factorial, so power 9 is less than 9 factorial, so power 8. And I would say that looks simpler than where we started, because the 8th root, the 9th root are awkward, tricky things. We've got rid of them in favour of powers, which are not quite so tricky as the roots. What can we do from here? We might keep on thinking about simplification. And the hardest thing probably that's left now is the factorials. And so I could say, well, what does that factorial actually mean? Well, 8 factorial means 1 times 2, etc., times 8. That's the power 9. And I'm saying that's less than 9 factorial, which is 1 times 2, etc., times, let's put it this way, times 8 times 9. That's all to the power 8. And the thing which you would, I hope, notice there is that there are lots and lots of common factors on the two sides, which I can cancel. There's many ways you could do it. So, for example, I could say to get rid of a lot of 1, 2, up to 8 factors, I could rewrite this in the following way by using power laws. That's an instance of the law xy to the power 8 is x to the 8 times y to the power 8. I can then clearly cancel a lot of things here. That will go. Most of that will go, leaving just 1 factor there. And so I'll write it this way. 1 times 2, etc., times 8 is less than 9 to the 8. What does that 9 to the 8 mean? Well, I've got multiplication only on the left-hand side. I've got a power on the right-hand side. Again, if we keep the aim in mind, we're trying to relate these two things to each other. So let's write that power as what it means, 9 times, etc. Where we can write it this way, just to make it quite clear, there are 8 factors here. Okay. Now what have we got here? We've got 8 factors on the left-hand side multiplied together. The factors are 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 factors on the right-hand side, all multiplied together. The factors are 9 times 9 times 9, etc. Is that actually less than that? Well, I hope it's now obvious that it is, because I can say 1 is less than 9, 2 is less than 9, etc., etc. Finishing with 8 is less than 9, so I multiply them all together. I get 1 times 2, etc., times 8 is less than 9 times 9, etc., 8 times. So this is true. Okay, so that's the sort of thing we could do for rough working for this proof. However, there is a big flaw with it, and we certainly can't present the proof in this way. Problem is this: I've started here, I've worked out something, I've worked out something else, I've worked out something else, and I've got down to this, something which I know is true. The problem with that is that for a proof I have to start with things I know are true and finish with the required conclusion. If you take this argument here at face value as an attempted proof, then I'm going to start off with that fact, which I know is true, except, of course, I don't know it's true. That's exactly what the question is. But if we take this literally, I'm starting with this fact, which is bad because I don't know it's true, and I'm finishing up with this fact. Well, what it comes down to is this is the fact that I have proved, or at least attempted to prove. But that, apart from the fact that we know this is true already, so there's no point in proving it, it also wasn't the question. That was the question. So, this is all very valuable in terms of rough working. Let me actually make that as a comment. Let's put it here, rough working. But it's absolutely worthless as a proof. And the thing is that it's the wrong way around. We need an argument which starts here and finishes here. We need to reverse all these steps. And that brings up the question, can they be reversed? Let's digress for a minute and let's ask about reversing steps in a proof. Can you just reverse any old step? Well, let's take some examples. For a start, suppose you say x equals 3. This is in your rough working. And you conclude from that that 2x equals 6. Okay, I've multiplied both sides by 2. Can you just reverse that in your proof? If I say 2x equals 6, I want to go in the other direction. I want to say x equals 3. Well, yes, I can. I can do that, because that's just dividing by 2, which is perfectly okay. Here's another example. Suppose I say x equals 3, and in my rough working, I square both sides to conclude that x squared equals 9. And now in my proof, I want that to go the other way. Is that valid? I hope you're clear enough on algebra to realize it's not valid, because if I'm starting with x squared equals 9, then I can only conclude x equals plus or minus 3. I can't be certain that x equals 3. However, there's nothing to say that our proof has to be our attempted rough working and nothing else. Suppose I had x equals 3 implies x squared equals 9 in my rough working, and in my proof I've got x squared equals 9, and I want to conclude that x equals 3. Now, it might be that there are other things I know about x. It might be that I can also prove that x is greater than 0. And in that case, this deduction here is correct. So the point I want to make is the following, and there's going to be a third example as well. But in my first example, in my rough working, I say x equals 3, therefore 2x equals 6. That just reverses. Easy, no problem. In my second example, in my rough working, I say x equals 3, therefore x squared equals 9. In my proof, I want to say x squared equals 9, therefore x equals 3, which is not correct. But if I can find out a little bit more information, x squared equals 9, and I also know that x is greater than 0, then it's correct to conclude that x equals 3. So this step can be easily reversed. This one cannot be reversed as it stands, but if you can find out a bit more extra information, then it will work. Here's a third example. Suppose I say x equals 3, y equals 4. Then I conclude x plus y equals 7. Okay, that's clearly correct deduction. Now suppose I'm doing my proof, and I want to reverse that. I want it to go the other way. In other words, I know that x plus y equals 7. I want to deduce that x equals 3 and y equals 4. Well, it's pretty clear I can't. If I have x plus y equals 7, then maybe x is 0 and y is 7. Maybe x is 1 and y is 6. Maybe x is 100 and y is minus 93. All sorts of possibilities. Could I fix that by finding a small amount of extra information, as I did in this example? It seems unlikely. If you know x plus y equals 7, and you want to know that x equals 3 and y equals 4, you would need quite a lot of extra information. It wouldn't just be a question, for example, of saying x is positive and y is positive, nothing like that. So in this case, reversing the step of your rough working to get the valid step in your proof would seem to be pretty hopeless. So there's these three things that you should think about when you're reversing steps from your rough working. Some steps can easily be reversed with no problem at all. Some can be reversed if you can find out an extra bit of information. Others, reversing the step would appear to be completely hopeless. You need to find out a lot of extra information, so much so that you're more or less making a different attempt, saying, well, this didn't work because we can't reverse it, and we'll just have to try something different. So, are there any problems with that sort of thing in this example? Well, let's work it out. If I go from here, starting here, I know this is true. Can I get back to here? Well, yes, because I have to multiply both sides by 1, by 2, by 3, 4, by etc. by 8 to the power 8 on both sides, and that's a valid step. Can I get this one? Well, that's just rearranging things according to index laws. Can I get this? Well, that's just using what is meant by a factorial, so sure. And remember, that one's out of it. That was an attempt which didn't quite work. Can we then get back to here? Well, to get from here to here, I have to take the 72nd power. So to reverse it, I have to take the 72nd root. And that, I hope people will realize, is something like this. Because to get from x squared equals 9 to x equals 3, I have to look at taking the square root of both sides. But that's not good enough because it would give me x equals plus or minus 3. But it's okay if I say I'm going to take the positive square root of both sides. So to reverse this initial step here, I'd have to take, going from here to here, take the positive 72nd root of both sides. Not good enough just to say the 72nd root, because there are two possible 72nd roots and only one of them is going to work. So, after all that discussion, this is the sort of thing which you might end up with as a proof. I'm going to start off with this information that I didn't actually write here, but I mentioned it. 1 is less than 9, 2 is less than 9, etc. That's clearly true. And therefore, if I multiply together the 1 by 2 by 3, etc., it'll be less than 9 by 9 by 9, etc. So I get that. Next step, I'm going to just rewrite that as a power of 9 on the left-hand side. 1 times 2, etc. times 8 is less than 9 to the power 8. And I'm going to do just what's indicated by my rough working here, but I'm going to do it in reverse. In fact, I think we can have a look at the whole proof now. So I'm going to multiply both sides by this 8th power of 8 factorial, and I'm going to simplify a bit at the same time. This times that one gives me that factor to the power 9. This one, at present, I'm just writing in. I'm going to rearrange terms by using the power laws on the right-hand side to get this. I'm going to introduce factorial notation. So 1 times 2, etc. times 8 is 8 factorial, and likewise for 9 factorial. And I'm going to take, not forgetting, as I just said before, the positive 72nd root of both sides. Not adequate to just say take the 72nd root of both sides. If I take the positive 72nd root of both sides, I get this, and that's the result that we were trying to prove. So, as we shall usually do, now let's find out some things that we can learn from this example. First one I'm going to mention here is go back to definitions, or expand the definition. What do I mean by that? Well, it's really a case of simplify. So let me put that in there as well. The reason is that what is a definition? A definition tells you what something means in simpler language. So by using a definition and replacing some terminology by its definition, you're making the language simpler, and so it stands to reason that that's going to be easier to deal with. And so, once again, not a definite rule. There aren't any definite rules in this subject, but a pretty good piece of advice. Go back to definitions. Where have we actually done this in this proof? Twice, I think. So first of all, we've got here the 1 by 2, etc. by 8 is equal to 8 factorial, because that's the definition of what factorial means. Secondly, how did I get this, the positive 72nd root of both sides? Well, by definition, the 8th root of a number is the number such that if you take the 8th power, then you get your number back again. That's probably, in fact, more clear if we look at the rough working rather than the actual proof. So here's the rough working that we did just before. And notice, what have I done with the 8th and 9th roots here? I've used the definition of what they mean. The 8th root of 8 factorial is the number such that if I take the 8th power, I get 8 factorial. And similarly here, the 9th root of 9 factorial is a number with the property that if I take the 9th power, I get 9 factorial. And I've done the 8th power and the 9th power of these to get rid of both of those roots. So here's the definition here of what's meant by an 8th root or a 9th root of a number. I've also used the definition of what's meant by factorial. These are just ways of simplifying. We've done other simplifications as well, for example, cancelling common factors. Here's a good piece of advice. A proof is often discovered by working backwards, but it must be written forwards. Now, why is that? Let's expand on that a little bit. That's just to firstly note, that's exactly what we did here. We worked backwards. We started with our conclusion and went back to our basic facts. But a proof must go the other way around. It must start with basic facts and reach a conclusion. Why do you often discover it by working backwards? Well, you could think about it this way. It's perhaps another aspect to keeping the aim in mind. If you're keeping the aim on your paper at the very start of your working, then that's clearly very much in your mind. And if you then try and simplify that, you can hopefully get down to something, a nice simple fact, which can be a basis for your proof. The point is that if you've got a complicated expression, you'll usually find that there's fairly limited ways that you could reasonably simplify it. Looking back here again, what could you do with that? It's hard to imagine you could do really anything much with that except try to get rid of the roots by taking the 8th power and the 9th power. You could simplify by writing out the 8 factorial as 1 times 2, etc. times 8. That would work fine. You'd probably need to get rid of the roots later. What it would come down to is that you did all of this just in a slightly different order. That could work just as well. But if we start with our conclusion, maybe it's a complicated inequality, and try and simplify it, we've usually got some fairly good idea of what we should do to simplify. Whereas, supposing we tried to start with the simple things and make them more complicated. In other words, we tried as our rough working to start here and then do all these things to get the desired result. That would seem to be very difficult in practice for a start. Why would you start here? It's quite clear they are true, but how do you know they're relevant? There's lots of things which are true. Why didn't I use the fact that pi is less than 9, for example? That might sound far-fetched, but the point I want to make is that you've got to have some reason for starting here. It's not a random choice. And the reason we have for starting there is that we've already done the rough working by doing it backwards. Furthermore, even if you did have that, how would you know what to do? How would you know to multiply them? How would you know to multiply by this factor? How would you know to take the 72nd root? And so on. So working backwards is often very helpful in discovering the paths that you need, but those paths must be traversed in the correct direction, in other words, forwards. Why is that? Why can't this here, here's our rough working again, why can that not be a proof? Well, I've been through this already, so just to recap briefly. Firstly, it's not a logically valid proof, because a logically valid proof would be starting with something that we know is true, and we don't know that's true. That is, after all, precisely what the question is. So this is an argument which starts with something we don't know is true, and it ends up with something that we didn't want to prove. So this is fine for rough working. In fact, it's very important for rough working. I would not really have much hope of discovering the proof without doing this rough working, but in itself it's not a proof because it's written the wrong way around. I'll give you a bit of a tip. If you have anything like this, which purports to be a proof, which ends up with this is true, or which is true at the end, that's normally a pretty good indication that you've got the proof the wrong way around. One more suggestion here, and that is something we've touched on before. So when you're writing out a proof, it's very important to write it clearly And so explain logical and technical steps in words. And just looking back at our proof, here it is again. So notice, whenever I do something, I give the reason why or I say what I'm going to do. So going from here to here, I'm multiplying both sides by 1 times 2, etc. times 8, to the power 8. And before I do it, I say so. So the person reading it knows what I'm going to do and can check that it's correct. I then say rearranging terms. Again, so the person reading it knows what I've tried to do and can check that I've done it correctly. I might perhaps even, it might have been a good idea to make that more explicit. Instead of just rearranging terms, I could have given as my explanation, using power laws on the right-hand side, I get this, and so on.